Okay, we are back. We are going to do 8.2. That's page 5 on the note packet, 8.2. So let's take a look. Again, the 5 steps that we summarized already. Test observed value minus expected value over the standard error is how you find your z-score. So let's jump to page 6 and do an example. I claim the average cost of men's athletic shoes is less than $80. After selecting a random sample of 36 pairs of shoes, I find the sample average is 75. The population has a standard deviation of $19.20. Is there enough evidence to support the claim at a 5% significance level? So let's take a look. First, the null hypothesis is that it equals 80. If you'd like, you could say or greater than or equal to 80. The alternative hypothesis, which was what was predicted here, was that it was less than 80. Now, our second thing that we do is we draw ourselves a pretty picture, standard normal curve. Since the alternative hypothesis is less, it's just a one-tailed test on the left side. Alpha is set at 5%. That was given. So we look up 5%, one tail, follow it all the way down to the bottom. It says Z is equal to 1.645. Since it's on the low end, below 0 here, we put a negative on it. Negative 1.645. All right, so now that's, I called it the Z. A lot of times you'll see it in my work as CV. That stands for critical value. It is a Z-score, but it has to be lower. It's a critical value Z-score, meaning that if it's lower than negative 1.645, we reject the null. If it's greater than, between 0 and negative 1.645, we fail to reject. So anything in the shaded area, reject. Anything in the unshaded area, fail to reject. All right, let's take a look at 3. You actually find your statistic, your test statistic. In this case, it's x bar minus the mean, the population mean, divided by standard deviation, divided by the square root of n. So that's 75 minus 80 over $19.20 divided by the square root of 36. That is negative 5 over 3.2. That is negative 1.5625. So negative 1.56 isn't enough to it doesn't, it's here with respect. Z is negative 1.5625. So it didn't fall into the shaded area. It fell into the unshaded area. Unshaded area means fail to reject the null hypothesis. At, in this case, the 5% significance level. So that means number 5, you put it in the context of the problem. There's not enough evidence to support the claim that the average cost is below $80. We're going with this. That the mean is $80, which is what we thought to begin with, the null hypothesis. So there wasn't enough evidence to conclude this. All right? So there is not enough evidence to support the claim that the average cost of footwear athletic shoes is below $80. All right. Cool. So let's look at example 2. Very similar. I claim that the average financial award at METC is $2,000 or less. If I sample 100 METC students randomly and the sample has an average of 1,800 and we know the population standard deviation is $500, test the claim at the 5% significance level. So let's see here. I claim that average award is $2,000. So we're going to say do all the same stuff here. All right, so let's take a look. So this one is worded a little funny. I claim that the average financial award at METC is, we're going to rewrite that a little bit to just say is less than $2,000. We're not going to work with less than or equal to. We're going to say less than $2,000. All right, so that is our alternative hypothesis. The null is that it equals $2,000, and the alternative hypothesis is that it's less than $2,000. All right, so that is again a one-tailed test. Our critical value at 5% is the same as it was above there, negative 1.645. That was looked up on the chart. This time we're going to put in our Z value here. What do we got? We got 1,800 minus 2,000 over, it was 100 students and 500. So what does that end up to be? Negative 200 divided by 50 is negative 4. Ooh. So that's 4 standard deviations below the mean. That is well within the shaded area here. So Z is equal to negative 4. So we reject the null hypothesis at the 5% significance level. So we are rejecting that it's equal to 2,000. In fact, based on this data, it is well within the shaded area. So we reject it all and conclude that There is enough evidence to support the claim that the average loan is less than $2,000. Now, be careful with this. Less than $2,000 is what we're testing. Lots of students accidentally work this in. They say, oh, we conclude that students get 1,800. No, 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 no. Remember, this is based on a population of 2,000. We're just checking to see if this sample shows us that it's less than $2,000. It is statistically significant, and it does show that it is less than $2,000, so we conclude that. We cannot work that 1,800 in without further study. You don't just get to replace the population standard deviation with your little sample of 100 students. All right? So notice they're all very similar. The structure is over and over again. So after you get the hang of it, hopefully this will come a little easier for you. All right, so now let's take a look at p-values. Page 7. So p-values are the probability of occurrence if the null were true. That would be the probability that we would get results like this. So let's take a look at page 7. Find the probability of the shaded area. Okay, so they gave us z was equal to 1.2. So for like number 4, z is equal to 1.2, and the null hypothesis is mu equals 14, and they want you to say not equal to. So if it's not equal to, let's take a look at that. That means it's a two-tailed test. So we're going to go with the two-tailed test and find the p-value. So for number 4, find the probability of the shaded area. Basically, we got a shaded area there, shaded area there. They're identical on a two-tailed test. They already told us that z was equal to 1.2, so we got a negative 1.2 there, a positive 1.2 there. We look up negative 1.2 on our chart. This is 0.1151. That means this is also 11.51%, top and bottom. And so when we want the p-value, that would be the shaded area. So the p-value in this case, we would just add those together. Or just times 2, like, because it's double. So there's a 23% chance. Or 2, 3. So if the null hypothesis were true, we would get results like this 23% of the time. That's how that is interpreted, all right? So take a look. There was a little typo on the notes on page 7 there. Example, suppose my alternative hypothesis, so that should say h sub 1, not h dot, is greater than 14, so it's a one-tailed test, so the null will make into equals 14. The alternative is greater than 14, and the z-score is 0.6. What is the p-value? So again, we just are going to look that up. We've got 0.6, and we want above that. So that's one-tailed test on the right side, right? And so when we look up 0.6 on our chart, it comes up as 0.7257. Well, that's clearly not 73%, right? That's above, and the chart gives us below. So we're going to do 1 minus 0.72, and that'll be 0.2743. That's our p-value. All right. So again, the interpretation of that is if the null hypothesis were true, if this were true, we would get results like this 27% of the time. So that's probably wouldn't be significant, greater than 14. The next one, they switch it up. They leave it almost the same. The null hypothesis is still equals 14, but this time the alternative hypothesis, again, typo, it says H0, it should say H sub 1. And that's not equal to 14. So it becomes a two-tailed test. And the z-score given is 0.6 again. So look, z is equal to 0.6, but also z is equal to negative 0.6. And so now you've got shaded areas on top and bottom, and it's the same shaded area that we looked up before. Well, it's 27%, 0.2743 there, and 0.2743 there. And so to find the p-value in this case, we would double that or add them together. 0.2743 plus 0.2743. And so that'll be 0.5486. So that is really not going to be enough evidence to reject the null, because if the null were true, we would get results like this 55% of the time. More than half the time we would get results like this. So it is very likely that's really strong evidence for the null hypothesis. The smaller this is, the more evidence it is for the alternative hypothesis. All right? And then there's a third one that looks just like those two here. With the 0.6 stuff here. Let me get rid of the 1.2. So the 0.6, third scenario here, z is still 0.6, but this time they want it less than for the alternative. Again, typo. There are 3 typos there. That's 14, but it should say h sub 1. The alternative hypothesis is less than 14, which means we take a look at that. Less than 14 would be down here, and the z-value that we calculated was negative 0.6. And so if it were 0.6, then below that would be 0.2743. All right. Oh wait, you know what? I might have interpreted that one wrong because it gave us the test statistic as 0.6. I did interpret that one wrong. Oh, here, real quick fix here. Don't add a negative to it. It's just right here. It's still a left-handed test. It's just that one's not going to require us to do anything other than look it up on the chart. So it is less than 14, but since z is positive, that was our test statistic we calculated to find these p-values. So it isn't looking it up on the chart where you just flip it to positive or negative depending on where it is. And so this one, when we look it up and we get 0.7257, we just stick with that. That is the p-value. So the 3 scenarios, greater than, boom, that was above it. When we looked it up and found 72%, we actually subtracted. Double-sided, then you do make one positive and one negative. It's a two-tailed test, and we add up those two shaded areas, the 27, 27, 54. And this one, we got to just look up directly. It was less than 14, and so it was here. That was our test statistic, was 0.6. And so it's all that shaded area below. All right. Great. Then One more example here. Lifeguard believes that the average age of all lifeguards is over 24 years old. To test this, she takes a random sample of 36 lifeguards, which has an average age of 24.7. The population standard deviation is 2 years. Find the p-value for this test. So they don't want us to actually run, they didn't give us a significance level and everything. They just want us to find a p-value for the test. So we're still going to do an alternative, a null and an alternative hypothesis. So let's get those down. So the null hypothesis and the alternative hypothesis here. The null is mu is equal to 24. The alternative is mu is greater than 24. And so here's what our picture would look like. We're looking at a z-score. Let's find our test statistic. It's 24.7 minus 24 divided by 2 divided by the square root of 36, which is 0.7 over 0.3, which is 2.1. So 2.1 standard deviations above the mean. We look up 2.1 on our chart and we get this 0.9821, but that doesn't look like it matches with this. This looks like a tiny percent and that looks like a big percent. That is actually from there down. So we want the complement of that. We're going to do 1 minus what the chart said, 0.9821, 0.0179. All right. So about 2% chance. So here's how we would do this. The p-value would be 1.79%, like 2 places to the right and then it's a percent. So what does that mean? This would be the statement. If the average age of lifeguards were 24 years old, we would get results like this. .79% of the time. So basically, if this are true, we would only get results like this about 2% of the time. So then when you skip down to the bottom of page 8, it says, can we support this claim at the 5% significance level? At 5%, we would reject the null. Because think about it, 5%, we would throw in, a line right there. That would be 5% would be the shaded area, and 2.1 would be within that shaded area. So we would reject the null and conclude the alternative. If they made it the 0.005 significance level, so what is that, 0.5%? Then we would fail to reject. This is 1.79%, this is 0.5%. So that would just be this little area would all of a sudden become the shaded area, and then the 2% wouldn't be in the shaded area. So this would be fail to reject at the 0.5, at the 0.5% level. At the 5% level, we would reject. At the 0.5% level, we would fail to reject. All right. Okay, next one we'll do is 8.3.